Hello friends, today I'm going to solve lead code problem number 1448, count good nodes in binary tree. Given a binary tree root, a node x in the tree is named good if in the path from root to x there are no nodes with a value greater than x. So what does it mean? It means that for a node to be good, the value in the node itself should be greater than any other values in its path from the root, right? So let's look at the example here. um, Here we have root 3. Here we this is the root, and we have a value 3 here. So a root is always a good node, right? Because it does not have anything in its path. So yes, so yeah, if we have a root and if the root is not null, then we have one good node, right? So then what we do here, if we consider the left node, um 1, then what we do, we compare the value in this node with the value in its root, right? So here, the value 1 is not greater than or equals to 3, right? So it is smaller than 3. That means this is not a good node. So if it is not a good node, then we won't add anything. That means this is not a good node, right? So then what we do, we move further to another left node, and we compare the value in this node not with 1, because for this, from the root 3 to its path, so here the 1, it is a smaller, right? So that means we have to compare this 3 not with the 1 but with the previous value, right? So yes, and this is greater than or equals to the root node, or the maximum value in its path from the root to this node, right? So that means we have one more good node. And after this, and we move to the previous the calling node, and if it had a right child, then we would have compared the one with the value in its right child node, right? So since it is not, then we again move to the main calling root node here. So now from here we move to the right subtree, and the first right node, right? Here it is 4. Then we compare the value in this node with the value in its root, which is 3, right? So and it is greater than the value in its root. That means this is a good node, right? So we add plus here. So until now we have 3 good nodes. So whenever we find a good node, that means the value is greater than the previous the its root value, then that means for now the 4 is the maximum in this path, right? So that means we call the left node now, right? And then we compare 1 with the 4, not with 3, because in this path we already found a greater number here, and this is 4. That's why we are comparing with 4. Unlike here in the left subtree, when we where in the left node 3, we compare the value with 3, not with the 1, right? Because the 3 was the maximum in this path. But here we already found a maximum node, that's why we are comparing 1 with 4. And here 1 is not greater than its root value, right? So that means this is not a good node, so we won't add anything here in our counter. And then from here we move here, right? And then like from here we again go to right subtree, and then we compare the value at this node with the previous value here, the 4, and this is greater than 5, right? So that means we add again here 1. So that means we have 4 good nodes in this tree, right? Yes, we have 4 good nodes, and that's correct. Now let's look into another okay. Let me remove this one, and yes. um, Now let's look at the another example here. Here we have the root node 3, right? So here we already have one good node, so we move to the left node, right? So here the value in this node is greater than or equals to 3, right? So that means we again have found a good node, right? So here now we again move to left. Here this time, since this was the greater than or equals to the it's the root node, so here we compare the value with 3, and the value here is greater than or equals to its root value 3, right? So that means we again found a good node, right? Yes. And then we move back here, so we will do this so we will only check the value in the left nodes if the left node is not null, right? So we have to check that, and then from here we move to right, and then we compare the value here with its root value, which is 3, and the 2 is not greater than 3, that's why we are not adding anything. And we have, and in this tree we found that the maximum number of good node is 3, right? So yes. Okay, so now let's code. Yes, so our first condition is here is that let's take the constraint. So we have the number of nodes in the binary tree is in the range 1. Oh, so it starts from 1, right? So we have at least one node, and that means, yeah, we have a root, and then it is not and that's not null, we at least have root, right? So okay, then if root dot left equals to null, and root dot right also equals to null, then we're going to return 1, because here in this case, if there was only 3, then it's a good node, right? If even if it does not have the left and right side, it is a good node. Yes. Then what we're gonna do, let's create another new function, and check nodes. Yes, and here yes, and then here what we're gonna do, so yeah, we already counted the so here, yes, so if the root is not null but its left and right child is null, then we return 1, right? So if it is not, then what we do, like we already have one good node, right? And then we return the good nodes written from the another function. So for here, what we sending the argument root, and we'll have to, within this function, we'll have to check the value in the current node with the value of its root node, right? So that's why we have to send the root dot val here. So here we have root and val, right? Yes. Okay. Okay, so since we are counting the good nodes, let's use declare a variable here, right? So total number of good nodes count is 0 initially. Now we check if root dot left does not equals to null. If it's not equals to null, what we do here, if the root left is not null, what we did, we compare the value in this node with its root value, right? So if root dot left dot val greater than or equals to its root node, and for this case this is val, right? If this is the case, then what we do, we add we add it to the total, and what we do here, we again call the function and here so we are at this node, and we again going to check its left node, right? So that means for this 3 1 we going to send root dot left comma root dot left dot val, right? Yes, yes. And if it is greater here, like here, if it is greater, then we compare with this value, right? But here it is not greater than the initial root value. So here in this case, so else what we do here, we add the value, but we are not adding 1 because the 1 here is not a good node, right? That's why we not add here, but we're going to call the function again, and we send left, but the value here will not be root dot left dot val here, because we'll have to use the maximum value, and here in this case this is val, right? So we use here val. Yes. And when we are done with the left node, we go to right node, and we'll follow the same thing here as well. If root dot right dot val greater than or equals to val, what we did, total plus equals to 1 plus check nodes. So if it is greater, then we send root dot right and root dot right dot val here. If it is not, then total plus equals to, we just without adding 1, we just send the root dot right, and here in this case it will be val, similar to what we did before, right? And finally, when we are done with this, we return total, right? So yes, now let's check our code. Oh, okay. Great, now let's submit our code. We are done, right?